Main sequence stars are a class of stars that occupy a significant portion of their life in a stable phase, during which they fuse hydrogen into helium in their cores. They represent the primary evolutionary stage for the majority of stars in the universe, including our Sun. Here's a detailed overview of main sequence stars. A main sequence star is a star that is in the phase of its life where it is fusing hydrogen into helium in its core through nuclear fusion. This process releases an enormous amount of energy, which counteracts the gravitational forces trying to collapse the star. This balance between gravity and internal pressure is known as hydrostatic equilibrium. Main sequence stars are categorized in the Hertzsprung-Russell (HR) diagram, a chart that plots stars according to their luminosity and temperature. The main sequence is a diagonal band running from the top left, hot, bright stars, to the bottom right, cool, dim stars. The defining characteristic of main sequence stars is the fusion of hydrogen atoms into helium in their cores. This process releases a tremendous amount of energy in the form of light and heat. Proton-proton chain, low-mass stars and stars like the Sun, hydrogen fusion occurs through the proton-proton chain, where hydrogen nuclei, protons, combine to form helium, releasing energy. CNO cycle, high-mass stars and more massive stars, hydrogen fusion occurs via the CNO, carbon-nitrogen-oxygen, cycle, a process that uses carbon as a catalyst to fuse hydrogen into helium at much higher temperatures. Mass. Main sequence stars can vary in mass from about 0.08 times the mass of the Sun, for the smallest red dwarfs, to over 100 times the Sun's mass, for the largest O-type stars. Temperature. Surface temperatures range from around 2,500 K for cooler red stars to over 50,000 K for the hottest blue stars. Luminosity. Luminosities can range from a fraction of the Sun's luminosity, for red dwarfs, to hundreds of thousands of times brighter, for massive O-type stars. Color. The color of a main sequence star depends on its surface temperature. Cooler stars are red, medium temperature stars like the Sun are yellow, and the hottest stars are blue. Main sequence stars are classified based on their spectral type, which is determined by the star's surface temperature. The classification ranges from the hottest stars, O-type, to the coolest stars, M-type. The types, in order of decreasing temperature, are O, B, A, F, G, K, and M. O-type stars, blue, extremely hot, greater than 30,000 K, very luminous and massive. These stars burn through their hydrogen fuel quickly and have short lifespans. B-type stars, blue-white, still very hot, 10,000 to 30,000 K, and very luminous. A-type stars, white, with surface temperatures of about 7,500 to 10,000 K. These stars are known for having strong hydrogen absorption lines in their spectra. F-type stars, yellow-white, with surface temperatures of 6,000 to 7,500 K, slightly hotter than the Sun. G-type stars, yellow stars like the Sun, with temperatures of 5,000 to 6,000 K. K-type stars, orange, cooler than the Sun, with surface temperatures of 3,500 to 5,000 K. M-type stars, red, the coolest and smallest main sequence stars with surface temperatures below 3,500 K. These include red dwarfs, which are the most common type of star in the universe. The lifespan of a main sequence star depends primarily on its mass. High-mass stars, massive stars burn through their hydrogen fuel much faster than smaller stars. For example, an O-type star may only live for a few million years. Low-mass stars, smaller stars, such as red dwarfs, burn their hydrogen very slowly and can remain on the main sequence for hundreds of billions of years, much longer than the current age of the universe. Sun-like stars, a star with a mass similar to the Sun, G-type, will remain on the main sequence for about 10 billion years. The Sun is currently about 4.6 billion years old and is halfway through its main sequence phase. A main sequence star remains stable due to a balance between two forces. Gravitational pressure. Gravity tries to collapse the star inward. Radiation pressure. The energy produced by nuclear fusion creates an outward pressure that balances gravity. This equilibrium allows the star to maintain a stable size and luminosity for a significant portion of its life. Stars eventually exhaust the hydrogen fuel in their cores. Once this happens, they turn off from the main sequence and begin to evolve into other types of stars. Low-mass stars. After the hydrogen in the core is depleted, these stars expand into red giants. Later, they shed their outer layers and leave behind a white dwarf. High-mass stars. These stars go through more dramatic changes, often evolving into supergiants. They may end their lives in spectacular supernova explosions, leaving behind neutron stars or black holes. The HR diagram is a fundamental tool in astrophysics that plots stars according to their luminosity and surface temperature. Main sequence stars form a continuous band stretching from the upper left, hot and bright stars, to the lower right, cool and dim stars. In the upper left, massive O and B-type stars are hot, luminous, and have short lifespans. In the lower right, low-mass M-type stars are cool, faint, and have extremely long lifespans. Low-mass stars. Red dwarfs are the most common and longest-lived stars in the universe. They are fully convective, meaning hydrogen throughout the star can be fused, extending their lifetimes significantly. Sun-like stars. These stars, like our Sun, are middle-aged main sequence stars. They are more massive than red dwarfs and have shorter lifespans. High-mass stars. Massive stars, such as O and B-type stars, are extremely hot, bright, and short-lived. Their immense mass results in rapid nuclear fusion, leading to quick evolution off the main sequence. Main sequence stars are the most numerous stars in the universe and are crucial to our understanding of stellar evolution. They represent a stable phase where stars produce energy steadily over millions to billions of years, supporting planetary systems and potentially harboring life, as seen in the case of the Sun and Earth. In summary, main sequence stars are the most fundamental and long-lasting phase of stellar evolution, ranging from small red dwarfs to massive O-type stars, with a stable nuclear fusion process at their core. They form the backbone of stellar populations and galaxies, and are essential to understanding the life cycle of stars.